Good day friends, the title of my presentation today is an introduction to robotics. Myself Dr. S.K. Saha. Today I will be covering the following topics: introduction, what is a robot, Indian scenario about robotics, robot subsystems, classifications, topics of interest, then REDIM, a software developed at IIT Delhi, student robotics to encourage how the student should be taking up robotics, and the conclusions. To talk about introductions, let us see the recent space exploratory robot Mars Pathfinder. So, here we will see that how Mars Pathfinder has gone to the space and explored for scientific research. So, here you see a small video clips of that how the spacecraft carrying the robot, and then it will be landing up. So, this is carrying and then it is landing up with the balloons. So, you will see it is packed inside many balloons. Here this is the balloon structure, inside that that Pathfinder is there, it will come out of that one, and that is this is the robot which is carrying out the scientific experiments. The mission is completed and a lot of data has been collected on that thing. You see the camera is coming out and taking pictures of different rocks and other things. So, this kind of technology has been developed in the area of robotics. So, it is still in the Mars land, as you see the robot is going. Then if you talk about more robots which are earth based, very interesting research, and we will see some of the shots. Like for example, here you will see some robots which are based on animals, or sometime
SMC rover, planetary rover with transformable wheels.
So, here you see that how a baby robot comes out from the mother robot and does some task.
Of a main body and unirovers which are detachable wheel units. Unirovers are grasping the connectors on the main body. Since the main body of SMC rover cannot move by itself,
so you see how it is doing the task.
When the rover reaches the destination, unirovers are detached from the main body.
So, from the main body it is detaching to do some other task.
Release the connectors and stand up by themselves. Next, the unirovers are start to transform into the locomotion mode. For the transformation, they move their arms like this. In the locomotion mode, they take this posture. It looks like a shape of a real tank toy.
So, it is showing how the robot is orienting its own way and doing some job.
This wheel unit can steer to change the direction of motion by changing the orientation of the caster at the wrist of the arm.
It is also showing how it is overcoming the obstacles.
With this extended arm, the rover achieves high mobility on land.
So, it is showing the climbing of the robots.
So it can climb over gaps easily compared with single-wheel locomotion units without any extended arm. To undergo several operations, the rover can transform into manipulation mode by pressing the ground with the arm.
So, from mobile mode it is becoming a fixed kind of manipulator.
The arm can be used as a manipulator.
As it is saying, the manipulator.
Now, in this video, the rover will pick up a stone. The gripper has 4 fingers which are
So,
linked.
picking up a stone.
At the end of the finger, there is a soft part for holding objects in a stable way. It can grasp various stones like this.
So, it is doing some task, collecting the stones on the beans.
Furthermore, in the manipulation mode, the rover can change its position with this motion called pivot turn.
So, you see how the gripper portion is used as a fix and then the base is moving.
After the mission, the rovers can grasp the connectors of the main body and they can become the locomotion wheels of SMC rover.
So, the task is completed, so it is going to the mother robot.
starting to study about cooperative learning.
Now they are cooperating. Many of those are cooperating with each other.
And also about their docking sequence.
So you see how one is connected with another to do some job.
Increasing small
How based on the
robot
insect's
agility
behavior,
and
the robotics have developed.
inspiration.
This video describes a new biologically inspired robot series called
They call it
Miniwings.
biologically
These
inspired robots.
30-centimeter-long robots can run at sustained speeds of over 10 body lengths per second and navigate challenging terrain. They are more compact versions of our larger WEG series of robots, which benefit from abstracted biological principles derived from cockroach locomotion.
You see how the
Cockroaches
cockroach
normally
motions have
walk
been
and
adopted.
run in an alternating tripod gait. In normal walking, they swing their legs high and in front of their bodies so that they can climb smaller obstacles without changing their gait. The previous WEG's vehicle uses one large drive motor to propel its 6 appendages
how interesting
in a
these
nominal
motions
alternating
are.
tripod gait. Its 3-spoked appendages, called WEGs, combine the speed and simplicity of wheels with the climbing mobility of legs. Its 6 axles are compliant so that its gait passively
So the video
adapts to
describes
terrain
the
and it can
technological
climb
development
larger
in it.
obstacles with its contralateral legs in phase. To be more compact, Mini-WEGs uses 4 WEGs that move in an alternating diagonal gait. Like the larger WEGs vehicles, it is battery powered and radio
How
controlled.
it is overcoming
and
the
it uses
obstacles.
only one motor to drive all of its WEGs. It also uses one micro servo for steering its front WEGs via a rack and pinion mechanism. The robot is highly mobile, maneuverable, and versatile. It can
These are
surmount
also called
obstacles
mobile
greater
robots.
than the radius of the WEGs, a difficult feat for wheeled vehicles. It can run forward and backward, upside down and right side up, and has a turning radius of 2.5 body lengths.
So how
On
it
both
is see
smooth
going
and
to
rough terrains, it
the
can
fields,
sustain a
how
high
it is
rate of
moving
speed
there.
of about 10 body lengths per second.
Now it will show the
Additionally,
jumping.
its robust construction allows it to sustain repeated falls from a height of over 10 body lengths and tumble down a flight of stairs with no damage. Some insects have other modes of locomotion to augment their
So now it will
walking
showing the jumping,
ability.
that
The
how
cricket beetle,
the
for
cricket is
example,
jumping,
can
and
jump
that
to
has been
surmount
adopted
obstacles of immense relative size.
in the robotics.
Jumping mini-WEGs has been developed based
See
on
how
this
it has
concept.
jumped.
It can surmount obstacles 2 to 3 body lengths high, such as a stair.
See,
As the robot runs, the single drive motor simultaneously stores energy in a
now it will
spring
jump
for
again.
jumping. After release, the mechanism is automatically retracted as energy is stored for the next jump. Deployment methods such as passive
Okay, so
glider
that way
jumps
there
under
are, I'll stop
consideration.
here for this
The
one
robot
and
survives
then
a 7-story
continue.
drop onto concrete.
So you see how the robotic technology has been developing. So these videos were taken from the video conference of 2003 IEEE Robotics and Automation Conference. This is to just give you some glimpse of how the robotics developments are happening. This one many of you will be aware of it. These are humanoid robots, came to India also for demonstrations. Now we come to the basic definition of what is a robot. A robot actually the word which has started in the this Rossum's Universal Robots in this act written by Karel Čapek in 1921. Robot is a Czech word, means work. Robota is a slave word, it is called menial or slave labor. Actually Rossum was a person in the act. Rossum wanted to create some machines which will listen to the human being and obey them as per their wish. When he has developed these machines, then he wanted to robot understand more and more. That means if he is thirsty, probably he thought robot should understand. So that means they are getting minds. When the robots started getting minds, they thought Rossum is exploiting them. So then he wanted, the robots wanted to destroy the design of Rossum, but then wanted to keep the drawing so that more robots can be created. In this process they wanted to go against Rossum, they fought with Rossum, and what happened in that commotion, the design or the drawings all got destroyed. So we do not see any robots after that one, after that act. However, people got scared of robots because of that story which went in that act. However, in 1940 onwards, Isaac Asimov has written many science fictions, and then finally he postulated some laws which I will come little later. Let us see, when we say robot, in our childhood we understand robots like a human being, as you have seen in the humanoid robots. However, most of the industrial robots or the robots which has been used until 10 years ago was of this type. These like our human waist, then we have a shoulder here, then the upper arm, then this is the lower arm, and then there is a wrist like our hand wrist. So, this is actually called programmable universal manipulator arm Puma robot made by Unimation Corporation in 1961. We see more robots. This is a robot made by an Israeli company. This is another robot which is made by Indian company, and the whole technology is developed in India except the motors and ICs which may not be available here. So, this is called a SCARA type robot because this kind of robots are used for assembly purposes, and for making the electronics boards to put the ICs on the boards, these kind of robots are extensively used. It gives very fast operations and very accurate operations also. This is another robot which we taught to write my name, for example, but it did not like my name, so it scratched it. Then there are space robots, right. We have just now at the beginning we have seen the Mars Pathfinder to do the simulations like capturing a target here by the robot arm, and then we will see the base how it is moving, which is not the case in case of industrial robots. More types of robots which are called wheeled robots, like for example, if you are going straight, you want to turn say right, then what you do is you just turn the whole directions of these two wheels and then it will try to turn right or left. But in this case the wheel itself has the rollers at the periphery, so that if you want to turn right or left, you give the motions on the wheels in such a manner that it will try to move in the left or right directions. Now, these are the robots which are with the legs and the wheels both, okay, as is a system supported with wheels and legs. More types of robots, it is called snake like articulated mobile robots. This kind of robots used in nuclear power plants to go in some areas to do some checking and things like that. These are called parallel robots. Now, why they are parallel? Because we have a parallel platform, a platform which is moving in parallel with this base. Not necessarily it has to remain always parallel, but since it is connected with some legs and it is called parallel robot, this kind of platform or the parallel robot is used as a flight simulator, where the pilots will be sitting here and these legs will be controlling the motion of the pilots, giving the feel of a aeroplane, whereas the screen in front of the pilot will show the different scenarios, different airport stuff. These kind of robots are also used as machine tools, which is shown here. Like here you can imagine that the moving platform is here, at the bottom there is a tool connected here, and then this tool will cut, the tool will move like this and it will cut a very complex shapes. Now, the international standard organization, that ISO definition of robot is an automatically controlled, reprogrammable, multipurpose manipulative machine with or without locomotion for use in industrial automation application. You see, I have underlined two words, multipurpose and reprogrammable. Any robot should have this characteristic. Now, similar definitions also exist, for example, Robotics Society of Japan or European Society of Robotics and others, and in each of their definitions, which I am not telling all the definitions here, these two words will remain common, because these are the two characteristics of the robot. Now, I was telling that Isaac Asimov has written many science fictions, because when he realized that this is an useful device or system, he said, okay, why we should always remember that RUR, resumes universal robot story, and be scared of robots. He said, okay, we can use robots to our advantage if we follow these rules. What are these rules or laws? Says a robot may not injure a human being or through inaction allow a human being to come to harm. The second one, a robot must obey the orders given by human beings except when such orders would conflict with the first one. And the third one is, a robot must protect its own existence as long as such protection does not conflict with the first or the second. So, in gist what it means, robot must obey the human being's orders, however, it should not obey such orders where it kills himself. For example, if a human being gives an order to a robot, destroy yourself, okay, it should not do it. No? So, that is the main summary of this thing. So, the first commercial robot came in 1962, It was by the Unimation, I was just telling you, Unimation Incorporation, and established by this person Joseph F. Engelberger, and he is also called as a father of robotics. And the first robot was installed in the General Motors plant. Now, looking at the Indian scenario, for example, there are many companies and the research organizations are working. Kinematics India Limited, I have just shown their robots. There are other companies like MTAB, BRC is a research organization, how about to make research. Then BEL, BML, CMTI, HMT, BHL, Provac Cybernetics. Many of them have initiated robotics activity for their own utilizations also. For example, BHL has developed their robot for welding purposes. Looking at the research organization, of course, IIC, Indian Institute of Science, IITs, Jadavpur University, CMRI, CARE, Center for Artificial Intelligence and Robotics, BRC again does also research. Industry use, if you look at industry use, a recent statistics which is published in International Federation of Robotics 2006 report, last 2-3 years about 450 robots are getting installed per year in India, whereas China is installing 3,400 per year and Japan is about 50,000 per year. And at this moment probably India would have about 1,500 robots in total used in different industries. Now, why we see even China or Japan, of course, far ahead, are using more robots than India? So, one of the main reason is unemployment. Now, when you talk about unemployment, one little old statistics we have, but it is a matter of debate. Now, Japan with 3,50,000 robots in 1992 had only 3% unemployment. Now, this is one should think whether the number of robots present in an industry and unemployment which is has a correlation or not. This is the statistics has been put in front of you. Other reasons for use of not much use of robotics in India could be lack of proper perspective, cheap labor, non-availability, high import cost or high investment at the beginning. More reasons could be only R&D supports are provided by the government like DST, DIT, companies' involvements are limited, absorptions rates are also poor. But we should ask a question, should India use robots? Does India need robots? If yes, then how? These are my answer, yes, yes, and we should do in a modified way, and if it is yes, how? Now, first thing we have to overcome this mindset, robotics versus unemployment, because any machine would also take up somebody's job, right? But should we use the machines in that case? So, this is the mindset we have to think. Also, we must think work in front of a furnace at 500 degrees C. Do we want our brothers or our parents to work in that kind of environment? This is a hazardous environment. Now, welding 2 parts for 8 hours per day for several years. If not, then probably we should use machines to do that job. So, robot should be treated as a machine rather than a human. Then only we should be able to forget the fact that unemployment aspect. So, here I am summarizing, it should be used in hazardous environment and then high precision applications which human being cannot achieve and export oriented product. So, indigenous design should be done, develop as required, make lot of awareness and think it as a machine as I have told you earlier. So, again I repeat, it should be used in a dirty, dull, dangerous, difficult jobs, and then we must think before we adopt a robotics, will the human being be jobless? If I mean in return to what we are gaining, then is the human being willing to do that job? Is a robot uses economic? So, it has to be seen in total perspective, not just only jobless or only it is giving precision jobs and things like that. So, in totality one must study before one decides to adopt robotics. So, now we come to different robot subsystems. Here as we see in the left hand side we have the motion subsystem which also call robot manipulator. Then this is a recognition system, the vision like our eyes. This is a computer which processes this informations and then gives the signal to the robot to do the task, and this is the object environment where objects are manipulated. So, we define motion subsystem, recognition subsystem and the control subsystem. Here we do the classification of robots. When we talk robots here classification, we are talking about only serial robots, industrial robots, like the robots which do the welding, painting kind of stuff. So, we classify as a Cartesian robot. This kind of robots are called Cartesian robot because their endpoint moves in a rectangular box in Cartesian coordinate x, y and z. Then we have a cylindrical robot, the end effector, that endpoint moves in the surface of a cylinder, we call it a cylindrical robot. Then the spherical robot, here it moves around the sphere, it is a spherical robot. Then the Scala type of robot is very similar looking to that cylindrical robot. Then the anthropomorphic arm, which is like our human arm. So, here I just wanted you to show some video clips which we have developed in a software called ADAMS, Automatic Dynamic Analysis of Mechanical System, because in our many institutions we cannot have so many robots to perform experiment. So, we are performing virtual experiments. Let us look at the cylindrical robot. So, you will see that the animation of the things which we have developed, and it is showing in 3 different views how it is moving. If you want to see another one, this is another one. Okay, I'll repeat this. It is moving in a 3-dimensional Cartesian space. Now, you can see how it is moving in different directions. Okay. Now, different topics of interest, when we do study on robotics or do research, these are the 4 major areas: kinematics, dynamics, control and simulation. In kinematics, it is the study of motions, as we know, the study of position, velocity, acceleration. Here we do 2 things: inverse kinematics and direct kinematics. Inverse kinematic means if the position of the end point of the robot is provided, but since control has to be done through the motion of the joints. So, to calculate those things, to give in the end effector positions and orientations to find out what will be the joint motions, like here the joint motions, right. In dynamic, on the direct kinematics, we do the reverse. If you give me this one, then I want to know what will be the end effector positions. In dynamics, we do the force studies, right. So, again in the inverse, what we do, if you give me this motions, then how much force I will be requiring, that I calculate, that is called inverse dynamics. In direct dynamics, if you give me this force, I want to find out how the motion will be happening. In control, this inverse kinematics and dynamics are used, because as I said, the motion is described in front of Cartesian coordinate, but the control happens to this one. So, we need to know how much torque will be applying here. So, that is for control. In simulation, without fabricating a robot, if you want to know that how a robot will behave, then we perform simulation, which is like a direct dynamic. That means, giving the torque here where it will move. So, here I explain in this diagram that okay, if this is provided, you go this direction to find out this information, that is called inverse. If you provide this information, if you want to know how it is moving, it is called direct. So, here is just a software screenshots I am showing it, which is developed at IIT Delhi. It is called recursive inverse dynamics of industrial manipulators. It does that inverse dynamics which I have just now defined. So, here for this Puma robot, we have done this analysis using this software. This is the input I have given, this is the output. For actually inverse kinematics, which we will study later, that it can have many solutions. Okay. So, these are the 8 solutions for this particular case, and this is one of the joint motions input we are providing to perform the dynamics. So, here I am giving the input for the dynamics, and this is the input in tabular form, and this is the plot. These plots have been checked with some other programs and they are working fine. Here I wanted to introduce student robotics. A student should build the robots and take part in different competitions. So, here IIT Delhi took part in 2006, and one of the robots considered to be good one. Here I wanted to show you just a video of one of the robots. So, you will see how they have built the robot and how it is turning right to unload those things, the boxes which they are carrying it. Okay. Doing this kind of job, the students get interested and they learn what robotics and how to interface different elements of robots. So, in conclusions, I have introduced robotics. Robot basics are explained, redeem software is outlined, robot connectivity is presented, and this redeem software can be downloaded from this site http www.angelfire.com then /sc/Saha. And thank you for your attention, and I hope you have enjoyed the lecture. Thank you. Good day friends, now I will discuss about the configuration of a rigid body, which is a part of a kinematics discussion. When you talk about configuration, it includes position and orientation. Why it is required? In a robotic system, for example, there are many bodies are here and this is the end effector of the robot. You want to control it by specifying x, y, z coordinate of say the end effector. Now, we want to correlate what is its motion with respect to the fixed frame here. Now, to do that thing, what we do is we fix up a moving coordinate frame on each bodies and then try to correlate say one moving coordinate frame attached to this body with respect to the previous one, then next one with respect to the previous one, so and so forth, and then we combine them together to get the transformation of that one. For that one, what we will do, first let us talk about orientation of one body with respect to the another one. To do this, let us consider that a moving coordinate frame u, v and w, I am not showing the w here, which is the third one, is attached to a body. Let us say the body is this duster here, right, and I want to find out its position and orientation with respect to the fixed one, which might be fixed say somewhere at this corner here. Now, when you say configuration, as I just said, it consists of position and orientation. Position means say position of the origin of this moving frame u, v, w. Okay. Orientation means how it is oriented, position means how it is placed. So, let us talk about the position first. When you say position of this origin, let us say it is indicated by a vector p and this point has a component p x and p y. So, we can represent this vector p in component form p x, p y, p z. I am not showing the p z component here. For the planar case, p z could be 0 or it could be some fixed value, that means this z distance, right. Now, since I have indicated this component or vector p along x, y and z direction of the fixed coordinate frame. I call it P is represented in a fixed coordinate frame. However, any vector should not depend on any coordinate frame, because vector is a quantity which has a magnitude and a directions. For example, the same vector P, I should be writing it as a P x, x, then P y, y plus P z, z. What does it mean? I have written this vector P in terms of the unit vectors along the axis of the fixed frame. So, this is my unit vector x along the direction of x, this is the unit vector along the direction of y. So, unit vector multiplied by this magnitude P x is constituting this vector, plus P y is the magnitude of this multiplied by this unit vector constituting this vector. Third dimension I am not showing it here. So, if you want for better understanding, let us put them 0 here, let us put them 0 here, but in 3 dimensional case, yes, z component exists, if exists then it is to be added. So, here I have not used any coordinate concept here, but now if you want to see that how these two are related, what I will do is I want to now get this information P f, this is a scalar quantity. So, it should not have any coordinate representation, and f. Now, x f means what? The representation of this vector in this fixed coordinate frame, which has this component x f is equal to 1 0 0, which means it has a unit value in this direction, no value in y and no in z. Similarly, y in f has 0 1 0, okay, which means no component along x, y 1 and z 0. Now, if you substitute those values in these equations, what will end up is P x, P y and 0. So, which is the same thing. So, now what we have seen, you can write a vector in a scalar quantity form, an array of numbers represented in a particular coordinate frame, and then you could write P is a vector sum of some other vectors, and now if we use a particular coordinate frame, you get the same result. However, one could choose some other coordinate frame, not necessarily this coordinate frame. Say if it would have been some other coordinate frame, say A, then you had to do accordingly what should be x in A plus P y, y in A and plus P z, of course, P z we are taking it 0 and then z in A. Now, in that case representation value will change, and so these elements will come out to be different. It is just like saying that okay, with respect to coordinate frame which is probably fixed it here, the distance of me is say some values 1 2 3, but if you choose a coordinate frame somewhere else, corner of that room, maybe those values will change, but vector position, that means my position, has not changed. So, this is the one I wanted to emphasize here. Now, I will proceed to the orientation representation. For orientation representation, there are many ways. Okay. Here we will discuss two different ways to representing. One is called the direction cosine representation and another one is the Euler angle representation. For the direction cosine representation, let me draw a fixed frame. I will show you with respect to planar case only, and the development will be exactly similar for the special case which is given in the unit. So, x y is the fixed coordinate frame and u v is the moving coordinate frame. Let us say the angle made by the moving coordinate frame, the u with respect to x is theta. Now, what we will do is to correlate these two coordinate frame, we will take a point say P here and this vector P, and this it has a component P u and this has a component P v. Then along the fixed frame it has a component P x and it has a component P y. Now, what we want to do is, knowing the values of P u and P v, I want to calculate what is P x and P y. Now, why it is required? Say for robotic application, I know the coordinates of a point in the end effector frame, which is at the end here, okay, maybe this and this. So, some point is here P, I know its information there, and then since all the control has been done with respect to the fixed coordinate frame. So, I need to know what is its, this is my point, what are its values with respect to the fixed coordinate frame. So, then what we need to do? We need to correlate the coordinates of this one with respect to the previous one, and then again transform it to the previous one, transform it to the previous one, so on and so forth, and come to the first one. Here I will just show you between two coordinate frame, one is fixed, one is moving. Now, one could write P x is equal to P u, this one is P u cos theta, I am abbreviating cos as C. So, cos theta means C theta. So, P u C theta minus P v sin theta. Okay. We can similarly write P y will be P u sin theta plus P v cos theta. This can be checked from this diagram. And so, P z, if you want to introduce, it is P w. We want to now put it in a matrix vector form, and then you will see this is cos theta sin theta 0 minus sin theta cos theta 0 0 0 1 P u P v P w. So, effectively what we got, representation of this vector shown in this frame, and then by multiplying this matrix we could get its values in the fixed frame. This matrix we denote as Q, or it is our rotation matrix. This vector P represented in the fixed coordinate frame, and this is vector in our moving coordinate frame, right. Now, these components can be shown to be, for example, this column cos theta sin theta 0, which is nothing but the components of a unit vector u along x direction and along y direction, is not it? Similarly, the second column is nothing but the component of v along x and along y, okay, so on and so forth. So, Q matrix is nothing but unit vector represented in the fixed frame, v the unit vector in the fixed frame, and then w in the fixed frame. Okay. So, the unit vectors along the axis of the moving coordinate frame, representation of those in the fixed frame. Okay. Now, these components are nothing but, so u transpose x and then this is u transpose y, u transpose z, then this is v transpose x, v transpose y, and then v transpose z, and then this is w transpose x, w transpose y, and w transpose z. What is the meaning of this transpose here? It is nothing but the result which you get doing this thing, that A transpose B is nothing but the projections of a vector on another vector. In this case, it is the projections of vector u on x. So, projections of u on x, this is x. So, this is nothing but cos theta. Length of this into cos theta will be this one, but since the magnitude of u is 1, so nothing but it is cos theta. So, this is a cos theta. So, u transpose x is cos theta, u transpose y is sin theta. Similarly, the others. Now, since these are called as the direction cosines of u, so the whole representation is called direction cosine representation. So, rep I am putting as an abbreviation for representation. This matrix Q has a very nice property. It is, one can verify that Q transpose Q is a identity matrix. It is a 3 by 3 identity matrix. You can try it out, Q transpose Q is identity matrix, and what does it mean? This means that the columns of this one or the rows of this matrix are orthogonal to each other. For example, if this is representing vector u here, this is representing vector v here. So, from this drawing we can see that u is perpendicular to v, that means u is orthogonal to v, and that is the reason that they are called the orthogonal matrix. Using this property, we can very nicely find out some other representation. For example, what we have seen, knowing P m, that means representation of P in moving coordinate frame to calculate in fixed, which means I know this and I want to calculate this one. But if I ask a reverse question, I know this, give me this. Okay. Now, since this is in a linear equations, algebraic equations, we can use linear algebraic equation formula to solve it, and what is that solution? So, this solution, so what we want is, we want to calculate P m knowing P f. So, the solution here is, it should be Q inverse, because in the form of A x equal to B, we know the solution of x is nothing but A inverse B. What is Q inverse? Let us come to our property here, multiply this equation by Q inverse in both sides. Since Q inverse is an identity matrix, so from this one we can see Q inverse is nothing but Q transpose. This is because of the orthogonal property of the matrix. So, this is nothing but Q transpose P f. So, when there is a rotation operations are involved, we can calculate one information from the other by just doing the transpose of the things. So, this is the direction cosine representation and a property of a rotational matrix. Next, we will go to the Euler angle representation. Now, one of the disadvantage here is, you see, in case of position, which is a 3 degrees of freedom, 3 coordinates were sufficient, but in case of rotations we need a 9 coordinates or 9 elements, but all of them are not independent, which means the 9 element must satisfy this equation. Okay. So, and if you break it, then you will see there will be 6 constraint equations. So, this means six scalar equations to be satisfied by the elements of Q matrix, which means I am using 9 elements to represent the orientation, out of which 6 equations have to be satisfied. In other words, it has a 3 degree of freedom, which we know from fundamental of mechanics that rotation has also 3 degree of freedom. So, the disadvantage here is we know 3 coordinates will be sufficient, however, I am using 9 coordinates. So, when you go to the other representation, Euler angle representation, we use that minimum 3 requirements, that means it has a 3 degree of freedom. So, 3 orientation representation should be sufficient, and that is the thing which we use in Euler angles. So, in Euler angles what we do is we consider the rotation with respect to x, y and z axis. Okay. For example, I have this say fixed coordinate frame, say x, y and z. Okay. And now, I want to represent here say u, v and w. So, this is my fixed, that is my moving one. What I do is I can reach from this orientation to that orientation through a series of rotation. Since it has a 3 degree of freedom, so with 3 rotations I should be able to reach there. Those 3 rotations we define with respect to say first about x, then about y or then about z or any combination of x, y, z. So, by rotating with respect to one of the axes, let us say I reach here, which I call it frame A, then I reach to another frame which is frame B, and then this is my frame F and this is my frame M. So, one rotation here, another rotation here and the third rotation here, right. So, one rotation here, second rotation here, third rotation. Now, since there are several combinations, one of the popular combination is called Z, Y, Z Euler angles. What is it? First, I rotate about z axis. For example, this duster, if it has a x axis along these directions, y axis along that direction and z axis along this direction. So, first I rotate about z. So, I rotate about z, right. Then, so my y has become in this direction. So, I rotate about y and my z has come now this, and then I rotate about z. So, z, y, z rotations I perform to reach from my one orientation to another orientation. So, this is called z, y, z orientation. Now, for getting the expressions now, because we have just now seen orientation is represented in the form of a matrix, and that matrix is required to transform the coordinate of a point represented in a moving coordinate frame to be transformed to the fixed coordinate frame. So, that matrix we require all the time. So, now we are interested in that matrix, that what is that matrix relating this. So, this Q matrix we are interested in, as we have found out in the earlier case. So, now first I am rotating about z axis, and let us say the rotation has been done by an amount phi. So, I have rotated from my this configuration by an angle phi. So, since it is a rotation about the z, one can see very easily that this is cos phi, sin phi 0, sin phi, cos phi 0, 0, 0, 1. Because it is a rotation about z axis, as we have seen in our direction cosine notation derivations that it is the this structure it follows. So, once it reached by an angle phi, I want to give a rotation about z by an angle theta. So, if you give a rotation about q y angle theta, then that means after I give the rotation phi, it has moved from f to f, and then I am giving rotation theta about y of frame A, so that it reaches to B, and that can be verified as 0 1 0 sorry. So, this is 0 1 0. So, this will be cos theta 0 minus sin theta 0 cos theta. This you can check it yourself in a manner. We have derived the direction cosine matrix, that knowing the coordinate in the moving coordinate frame represented in the fixed coordinate frame, rearranging the things and got the matrix structure. You could try this one. Then the final. So, we reach to B now, then we give another rotation with respect to the z axis of B frame, so that we reach to the final frame, and since it is in z rotation, means rotation about z axis, it will be a similar structure cos psi sin psi 0 minus sin psi cos psi 0 0 0 1, right. So, what we have done here is what is also known as elementary rotation. I am rotating with respect to only one axis, first about z, then about y, then about z again. Now, if you want to find out, so these are my elementary rotation about z, about y, about z. Now, if you want to find out what is the total rotation, then this is the definition. The total rotation q is nothing but q z phi q y theta and q z psi. Okay. So, this any composite rotations can be composite rotation can be defined as a multiplication of the elementary rotation. Now, if you now multiply these three, you will be able to see the final result is shown here, cos phi, cos theta, cos psi minus sin phi, sin psi. I will not be writing all the components because they are already there in the unit. I will just write the first column sin phi cos theta cos psi plus cos phi sin psi minus sin phi and cos psi. So, similarly, here element, here element, here element, here element, here element, here element. So, this is the representation of rotation matrix Q of the moving frame with respect to the fixed frame, where the intermediate rotations are represented using the Euler angle. You could also verify that this is also following the property Q transpose Q equal to identity matrix. Now, I wanted to point out this column is nothing but the which we have done while deriving our direction cosine. This represents this, if there is a unit vector here u, its components along x along x, along y and along z, where these things are the Euler angle rotations with respect to z, y and z. Okay. So, these are the two rotations. So, now let us take a simple example to show you how these things can be utilized. So, we will show, first I will show the example which is say vector rotations. Okay. So, how the orientation representation which means let us say I have this coordinate frame, fixed coordinate frame y, and I have a vector, let us say this is the initial vector, okay, and we denote it is a p prime vector, and then it moves to a new positions which we say vector p through and rotation theta. Okay. So, what we do is basically what we have done here is we have rotated vector p prime by an angle theta about z axis to get to the new positions p. So, this is we can say point p prime to point p. Now, if you want to now write this thing p prime in the fixed coordinate frame has component, we use the way we have done it earlier p z prime, and then p in f has p x, p y and p z, right, which means this and this. Now, the way we have derived our direction cosine matrix, writing the moving coordinates and relating to the fixed coordinates, similar way if we write p x can be written as p x prime cos theta, then minus p y prime sin theta, p y is equal to p x prime sin theta plus p y prime cos theta. So, then p, this structure is the same as we have done at the beginning, that p in f was so what we have seen the moving coordinate frame here, okay, a vector representing moving coordinate frame, this is nothing but our p prime, the old one. So, if you compare our earlier, so if a point p is represented in a moving coordinate frame, if you want to convert into a fixed coordinate frame, you multiply with a rotation matrix q, and that rotation matrix also transforms a old vector transformed to a new vector. Okay. So, this is one of the applications of the rotation matrix used to define the rotation of a vector, that what is its old representation and what is its new representation. Okay. Now, I will introduce a concept which is called homogeneous transformation. So far we have seen a rotation of a coordinate frame is related with another with respect to a 3 by 3 matrix, right. But a transformation, when this body is moving in a space, it is not only rotation, it is rotation as well as translation. So, two components we have discussed. So, again with respect to a planar case, I explain. So, earlier our origin of the moving frame was here, now I am shifting it to somewhere here u and v, right. And let us say this notation I will use as vector O, that means origin of the moving frame. So, if you want to now try to derive that rotation transformation matrix for the purpose of transforming the coordinate represented in one coordinate frame to another coordinate frame, we use the same strategy. Let us say this is p u here, p v here, p x here, and then p y here, right. So, if this origin was here, we know its representation was very simple. It was p u cos, if this angle is theta, then it is cos theta plus p v sin theta, and p u y is equal to p u sin theta minus, this is minus, this is plus p v cos theta, right. Now, since I have shifted the origin, so this part has to be added, right. This is O x and this is O y. So, plus O x plus O y. What it means? Coordinate of this point P in a fixed coordinate frame, that means this distance is p x is equal to whatever we have done with only orientation, no origin shifted, we have just added this one. Putting in a vectorial form, one can write P represent in a fixed frame is equal to Q represented P is in moving frame plus a shifting. But this is no longer only a matrix transformation added by some vector. If we want to program it and for a unified operations, if you want to do it, then there is a way that we can consider it only matrix multiplication. How it is? It is as follows. Now, let us go from here and do certain tricks here. P in F is equal to P in M, right. So, Q, so P F is equal to Q into P M, but now as I say something has to be added. So, this is O F to be added, because O x and O y is nothing but O in F is O x O y. You see, many times I am skipping z, because when I am doing planar I am considering it 0 or some fixed value which is not immediate interest to us. If I have to get this information, so what I need a scalar quantity 1. Now, this equation is written in a matrix vector form. However, right hand side I have a 4 dimensional array, it consists 3 one scalar. So, it is a 4 by 1, this is a 3 by 1 and this is a, so this is 3 by 3, this is 3 by 1. So, this will be 3 by 4. Mathematically it is perfectly all right. However, when you are programming it, many times we want to put matrix multiplication in do loop. So, we wanted to see whether this matrix sizes and can be kept similar. For that, what we do is we put a 1 here, then we add a rows of zeros and then 1 here. So, effectively what we have done is first operation is giving me the result which I am interested when a moving coordinate frame is not only rotating, but also translating. Next one what I did, I put 0 0 0 which will be multiplied giving me 0 to be added with one scalar 1. So, 1 is equal to 1. Now, I have converted it to 4 by 4 matrix and this I have converted to 4 by 1. So, effectively I am taking into account only 4 dimensional vectors, 4 dimensional vectors and the 4 by 4 matrices. So, in a computer I have to talk about when it is a vector array it is a 4 dimensional, when it is a matrix array it is a 4 by. This kind of matrix is called homogeneous matrix, which takes into account both position plus orientation. So, what we have done in orientation, that a 3 dimensional position was converted into another 3 dimensional position, moving frame to fixed frame multiplied by 3 by 3. If you want to convert the positions also, so we multiply with a 4 by 4. This is called homogeneous transformation and we represent with a T. For the orientation matrix 3 by 3, we have seen that it has this property which is called orthogonal property, right. Does this matrix, the homogeneous transformation matrix, has this property? I am asking this question now. T transpose T, is it 1? That means 1 in a sense. Here I am 1, I am writing for. Okay. If you check it yourself writing its component, you will not find out that this is true. So, what we write? No, this is not true. Okay. However, as we have been trying to find out relation, this is Q in P m, we from here we could calculate P m as Q transpose P f. So, if I ask a similar questions like here, if the whole vector is represented is P prime now, if I write P prime to denote this 4-dimensional vector as T into P prime m, then in a similar manner, if I want to find P prime in M is equal to P prime in F, of course, from the linear algebraic equation we know this will be T inverse, but this T does not have homogeneous orthogonal property, right. So, we cannot write it as a T transpose. So, then it is a difficult task. Do we need a computer to do this? Certainly not. We will just now see that this has a very simple representation. So, what is T inverse? One can find it out from this T transpose T is equal to 1 4 by 4. If you write its expressions Q, this is O, this is 0 transpose, okay, that 0 0 0 I have written, this I am indicating is phi to indicate 0 transpose, right, and this is 1. So, this to be transpose. So, this is the expression of T, this is the expression of T, I want to do T transpose. So, this should be Q transpose, this will come here, it will become phi means 0 0 0 column, this will become O transpose and this is 1, and then this is Q phi, then this is O 1 should be equal to identity matrix, which means this will be 3 by 3, this will be then phi, this will be phi transpose, this is nothing but 4 by 4 identity. So, now if you perform these operations and equate in the right hand side, you should be able to verify very easily that T inverse is nothing but Q transpose minus Q transpose, then this O, and then this is phi transpose and 1. This is to be written, this is O vector. Okay. So, now one can verify that this T transpose T should be equal to. So, this is the expression for T inverse. So, if you have a 4-dimensional array representation or homogeneous representation of the vector P in the moving coordinate frame, which relates to fixed frame by this 4 by 4 matrix T, and if you want to find out the reverse expressions, we have to do T inverse, and that expression of T inverse is this one. Okay. So, now for a robotic system, when we have to do the transformations from one frame to other, we have talked about rotation case, that if we have elementary rotations and from there if we want to find out the composite rotation, it is a series of multiplication of those rotation representation as it is happening. Like in Euler angle representation, we have seen that composite rotation q is q z by an angle phi, q y by an angle theta, and q z by an angle psi. Similarly, if we have a series of rotation and translation both, which means in a robotic system, if I have this kind of series of rigid bodies, every body I fix a coordinate frame, and one coordinate frame I can represent with its previous coordinate frame by a rotation and translation represented by this homogeneous transformation T 1. From there I do T 2, so and so forth I go. So, this is from 1 to 2, this is n minus 1 to n, and then I can find out T n minus the way it is been for the orientation composite representation. So, this will be using it for our